Climate change is a present and fundamental crisis, primarily driven by human emissions of CO2 and other greenhouse gases. In this practicum project, I aim to dig deeper into these issues by explicitly identifying the key factors contributing to the increased emission. I will go over the background, project's overview, timeline, dataset overview, and data exploration, as well as clustering analysis and findings and result and future step. Greenhouse gases play a critical role in the Earth's climate system. These gases naturally trap some of the sun's heat, helping to maintain a stable climate that is suitable for life. However, human activities have significantly increased their concentration in the atmosphere. For instance, the National Oceanic and Atmospheric Administration Global Monitoring Laboratory reported that atmospheric CO2 level reached approximately 430 parts per million in early 2025, a significant rise from pre-industrial level of around 280 ppm. Similarly, methane concentration have increased dramatically, um, more than double the pre-industrial level. These increased greenhouse gases concentration enhance the natural greenhouse effect, leading to global warming and significant changes in climate patterns. The consequences include extreme weathers, rising sea levels, ecosystem disruption, and adverse health effects. Addressing these increased greenhouse gases is thus critical important for environmental sustainability, economic stability, and human health. As you can see from this chart, the atmosphere increase in CO2 in weekly averages observed at Mauna Loa, Hawaii. The preliminary weekly, monthly, and daily averages at Mauna Loa for the last year are included on this graph. This project will apply unsupervised learning techniques to explore and analyze greenhouse gas emission data, aiming to review patterns and insight without predefined labels. Furthermore, the analysis will utilize principal component analysis or PCA to simplify complex multidimensional emission data into easily interpretable visual forms. Additionally, the project aimed to identify countries or sectors that exhibit unusual emission patterns. The timeline is divided into 8 weekly phases, providing a roadmap from initial setup to final presentation. Looking at the dataset, there are about over 44,000 rows and 22 columns of variables. There are key columns such as sector metrics, financial metrics, emission metrics, and country statistics. Prior to clustering analysis, EDA is conducted to investigate and understand the relationships among greenhouse gas emissions, country-specific statistic, financial metrics, variables to examine data patterns, trends, and correlations to gain insight into how these factors interact with each other. First, let's review emissions trends over time. This chart illustrates average emissions per year. The sharp decline in emissions from 20 to 21 was due to the global lockdown of the COVID-19 pandemic. Since then, these upward patterns could reflect economic recovery, increased reporting transparency, or growth in high emission sector. Let's look at the distribution of Scope 3 emissions with a histogram to understand the distribution and potential skewness. The distribution is highly skewed to the right. A log scale transformations help visualize the spread of the data effectively. The skewness indicates that most entities report relatively lower emissions amounts, while a smaller number of entities have significantly higher emissions. Higher emission outliers disproportionately contribute to the total emissions. In reviewing Scope 3 emissions by primary sector box blocks, uh, we can see some sectors display significantly higher median emissions and a broader range indicating that emissions are strongly sector dependent. Can we pinpoint specific contributors? Let's look at the emissions by sector over time to uh, identify identify a sector with the highest average emission rate over time, and that is sector 34, um, which is oil and gas processing. Sector-specific strategy may be needed to curb emission effectively. A heat map has been created that shows the relationship between all variables. Uh, the heat map clearly identifies smaller section of strong correlation between financial metric and emissions. We will drop some variables with no inherent ordering or meaningful distance for clustering, and we will keep the factors that logically contribute to emission pattern. Smaller heat map illustrate relationship among greenhouse gas emissions, country statistic, and financial metrics. There is a strong positive correlation amongst financial metrics, indicating that financial independencies emission have notably weak correlation with most financial metrics, suggesting factors beyond direct financial size or profitability alone might influence emissions. Additionally, country-level metrics strongly correlate with emission metrics. Clustering analysis. The ELBO method was applied to choose the optimal number of cluster. Clustering analysis has been performed to find groups of countries a company based on their emissions. Appropriate features were selected because they directly relate to greenhouse gas emissions and help explain emission patterns. Therefore, using categorical codes that don't have a clear order or meaningful distance would add noise to the model. At this point, the silhouette score and the PCA plot of the model both shows that the clustering of 11 yields the best result. A scatter plot is used to visualize the result of a k-means clustering analysis, specifically showing how data point are clustered based on the sector ID after applying PCA or dimensionality reduction. Interpreting the cluster result colored by sector IDs. First, colors in the plot denote different sector IDs, effectively illustrating how entities for various sectors are distributed across cluster. Every cluster has a diverse mix of sectors rather than one cluster being dominated by a single industry. This diversity implies that clustering is influenced by a combination of factors such as market capitalizations, revenue, scope 3 emission, GDP, and populations rather than just industry type. Some sectors appeared across multiple clusters, showing that emission behavior varies even within a single industry. For example, entities with the same sector may differ in the emission behavior depending on their geographical and economic context. A few points are positioned far from the center of the cluster formation, suggesting they are outliers. These might be countries or companies with extreme Scope 3 emissions, exceptionally high or low market cap. In conclusion, this diversity implies that clustering is influenced by a combination of factors rather than industry type alone. The plot reviews that complex interplay of sectoral, economic, and national characteristics shape emission behaviors. Additional analysis is required to gain more insight. Ultimately, the unsupervised learning approach effectively illustrates the multi-dimensional patterns beyond simple categorical grouping. It would be valuable to identify which sector dominate each cluster by cross-tabulating cluster versus sector ID, gaining insight into which industry contribute to the most uh, to each emission behavior group. This can support targeted policymaking and sustainability strategies tailored to the emission profile of different clusters. Thank you very much. This discussion aimed to provide valuable insight into the importance of sustainable strategy to address greenhouse gas emission. Thanks again.